working on sulfur isotopes for his PhD thesis. Then he moved to Carnegie Institution of Science, Geophysical Laboratory for his postdoc. And then he moved back to Europe, working in Tübingen University in Germany, where he tasted some German beers and wines. And after that, he gave up Europe and moved to UCLA and working with Edward Young. I think that's the work that is presenting today, coming from. After that, then he moved back to France. So now he's enjoying French food every day. So with that, I will give the rest time to Jabrane. And this is just a semi-formal seminar. So it's just like a chat with your friends about the science. So later on, we will have, please leave more time for our audience for interactions. I do believe the audience has a lot of questions to ask. So with that, I'll give time to you, Jabrane.
Okay, thanks. Thank you, Jody. And thank you to have invited me to give a presentation at the Zhejiang University. Correct me if I'm mispronouncing it. So this is an honor, and I will be today presenting some new data that we have, and I will discuss this new data that we have acquired at UCLA over the course of my postdoc that ended now a little more than a year ago. And I will be talking about how new clumped isotopologue data can help discussing the origin of nitrogen in volcanic fluids and what it tells us on the origin of nitrogen in the planet. So the motivation for this study is to understand what is the origin of volatile elements in planets, and especially in the Earth. And we care about this question because volatiles are drivers of planetary habitability, right? Thanks to volatiles, we have an atmosphere, oceans, and the possibility to habitate life. So nitrogen, in the specific case of this element, is striking because it's the main constituent of the atmosphere. There is about 78% nitrogen in the air that we breathe. But there's also some nitrogen in the Earth's mantle, in the deep Earth. In fact, the question that is often asked in the community is, well, what is the origin of that nitrogen that occurs in the Earth's mantle? So to look at that, we, as geochemists, we often turn to meteorites because we think that they have evidence that they were the parent bodies of the Earth. Now, it's not clear which meteorite was the parent body of the Earth, if there was only one, or if there were several. But usually we look at meteorites to understand what the origin of any given element might be in a planet. So here is a forest plot, which have nitrogen concentration on the x-axis and nothing on the y-axis, where the nitrogen concentrations of chondrites are shown. You see that there's basically about 1,000 ppm nitrogen in most carbonaceous chondrites. For some, it goes to about 2,000 ppm. So it's about 0.1% to 0.2% nitrogen. In contrast, the Earth's mantle and the Martian mantle have less than 1 ppm nitrogen. So there's this severe depletion in a nitrogen concentration in planets compared to the parent bodies. Here is another way to look at the origin of any given element in a planet. It's to look at its isotopic weight or isotopic ratio. For that, we turn here to the 15:14 ratio. There's an issue with the sounds. Okay. So anyways, we can turn to the 15:14 ratio to track the genetic link between chondrites and a planet. So here it's done on the second plot on the left side that shows the same samples, the very same samples, against nothing in terms of y-axis. And you can see that the 15:14 ratio varies by a lot, by about 150 per mil. So it's a variation by about 15% of the isotopic ratio of the different asteroids in our solar system. and that the Earth and Mars are somewhat in between various components that seem to contribute to nitrogen in the solar system. So obviously, any geochemist would plot the nitrogen concentration data versus the nitrogen isotope data from the chondrites. And when you do that, this is what you obtain. So forget for a minute the blue samples, which are unique. They're strange for many reasons. So we can think about them differently. If you focus on most of the samples, you see there's this two-component relationship that indicate that within the solar system, there might be two components. There's asteroids with low nitrogen concentration that tend to have a low nitrogen isotopic ratio. They are around here. And they appear to be mixed with a component here that brings nitrogen so that it increases the nitrogen concentration to almost open 2% here, or 2000 ppm. And this component is associated with a positive nitrogen isotopic ratio. Now, if you plot the Earth and Mars on that space, you see that first, the Earth and Mars are around 0. They don't really plot towards minus 50 or 40 like the depleted components are. They don't plot either at plus 50 like the enriched component are. So they are somewhat in the middle, but in terms of nitrogen concentration, they're extremely depleted. You see, you can compare 1000 ppm to about 0.1 ppm. So there's something like 5 orders of magnitude of nitrogen depletion. So something happened in planets that not only changed the isotopic ratio, but also led to a substantial volatile loss. So the origin of nitrogen in a planet is quite unclear. It could be a mixture of various types of chondrites, and there's obviously some volatile losses that have taken place, and therefore it's a challenge to reconstruct what the origin of nitrogen may have been right after the formation of the planet. So, of course, it's never that simple. There's layers of complexity, and in geochemistry, Earth scientists have used the fact that on Earth, there is something that's called plate tectonics. So in addition to the fact that planets have complicated origins, in the Earth, reservoirs exchange over 4.5 billion years of Earth's history. So the observation for nitrogen is even more mysterious, because when you look at the delta 15N of the mantle that we can observe today, you obtain values that are about -5 per mil, right? You have the convective mantle has a delta 15N that's low. But the surface, any nitrogen that's in air and in the continental crust have a distinct isotopic ratio that is at about, on average, at about +2 per mil. So there's this possibility, because these reservoirs are in disequilibrium, they have a distinct isotopic composition. There's the possibility that their primordial compositions have been erased by 4.5 billion years of exchange between the surface and the mantle through subduction. So as you all know, the Earth is a dynamic planet, and plate tectonics redistributes components from the surface to the mantle via subduction, and from the mantle to the surface via volcanic degassing, right? So there's an exchange between these reservoirs. And if you look at the present day composition of the mantle and air, or the mantle and the surface, some people have suggested that these differences are in fact inherited from prolonged exchange between the reservoirs from starting composition that were even more extreme, right? So with a mantle that would look like one reservoir, and air that would look like a completely distinct reservoir. And over time, these reservoirs would have exchanged. The constraints, however, on these evolution models are extremely loose. To give you a few ideas, we don't have any fundamental observations on, for example, the nitrogen concentrations in the mantle. It's not that well known. There's mantle reservoirs that have not been addressed. And therefore, we lack some fundamental observations to constrain that speculative evolution model. So in order to put some actual science onto this proposition, we have to look, as geochemists, we have to look at the flux exercise. Basically, whether an element is exchanged or not between two reservoirs depend on the fluxes of exchanges between these reservoirs, which here are represented as the arrows, right? So you see the degassing arrow here is yellow, the subduction arrow here is taken as blue, and there's a an arc degassing arrow here that is green. Well, knowing these arrows is one fundamental issue that we need to constrain. When we take the few constraints that we have right now on the nitrogen cycle, this is what the cycle should be looking like, right? You see the orange degassing, flux from the deep mantle is supposed to be very small. That's normal because the deep mantle is non-convective. It doesn't really contribute a lot to the accumulation of volatiles in the atmosphere. The degassing from the convective mantle is substantial, but it's not close to be as huge as the subduction arrow based on the current understanding of the literature. So it looks like basically there's a disequilibrium in the nitrogen cycle where components from the surface should be experiencing right now, they should be trapped in the mantle via subduction. And what we're seeing today should not be indicative of what the nitrogen cycle was in the past, because this cycle seems to evolve, right? This arrow of subduction is massive, so subduction from air is being lost to the mantle, right? And that's something that's an important requirement of the flux analysis. Now, if you remember, if there is such an exchange between air and the mantle, then why is there any difference in terms of isotopic ratios between these reservoirs to begin with? So this is the types of questions that we don't truly understand. So today I'm going to be showing some new data for nitrogen, and I will provide tangible, fundamental new constraints on the nitrogen cycle. I will talk about the delta 15N, which is the nitrogen isotope ratio. I will use data in subduction zone, but I will also use data in the deep mantle reservoirs that may or may not contain primordial gases like nitrogen. So we'll discuss the isotopic composition of the subduction zones and of deep mantle reservoirs. I will also use the helium flux to bring another fundamental constraint on the nitrogen cycle, and that's because the helium cycle is very different. There is basically, you can see here the arrow of helium subduction. It's tiny. Helium is not recycled back in the mantle. That's the one element that we know unambiguously does not experience recycling. So measuring nitrogen helium ratio will be a good indication of whether or not there's nitrogen addition to a mantle source via subduction, right? Because the nitrogen addition will occur without any helium subduction. So we'll be again looking at plumes and deep mantle and subduction zones. So I will be providing two new fundamental observations, delta 15N and nitrogen helium ratios of the mantle source. So I will be talking today about 4 locations. 3 of them are hotspots or intraplate magmatism: Iceland, Yellowstone in the United States, and Eifel in Germany. I will also be talking about the Central American subduction zone here as a case study of what may happen in subductions. So typically what we do in this community, we use basalts. And that's because basalts are the result of the partial melting of the mantle. And so they trap mantle volatiles. We can study the composition of these mantle volatiles. Typically, we need glassy rims, like you see in this spectacular photography, where you see the outside of a pillar lava that was quenched by cold seawater. And using these glassy rims, we can constrain a lot of aspects of mantle geochemistry. However, for the sake of this study, we did not have access to any glasses because arc magmas and plumes rarely provide this type of unique samples. Oftentimes, magmas are erupted in air and they're not experiencing any quenching and they're experiencing degassing. So we do not have access to these powerful types of samples. What we do, the opposite of what, what we've done in the study, instead of using undegassed magmas, we've used the complement, which is degassed volatiles from the magma, as known as volcanic gases. So here you can see pictures of an eruption in one of the volcanoes that we've studied in Salvador in 2005. This is the type of sample that we would like to be having, right? Samples that are directly coming off out of an eruption. Of course, we don't have access to this because, and no geologist, as great as they may be, no geologist would probably survive collecting this type of samples. So what we actually are left with are hydrothermal samples, samples that are associated with the passive degassing of volcanoes and that have some interaction with the hydrothermal system. There's here a picture of one type of sample that was picked on Iceland, where you can obviously see the water vapor that's being warmed up by the volcanic activity at depth, right? So there's a mixing between water and volcanic gases. Some of the samples also are going to be springs in volcanic regions. So springs are very unimpressive. This is here a video of two students that I have collaborated with for this project that are sampling a hot spring in Germany. You can see that this is not a very scary sample. It's very easy to sample. But however, you would be surprised by how precious this sample may be for this study, in fact. Sorry. So what we have, just to summarize before I show data, what we're dealing with is magmatic samples that correspond to degassed volatiles that are produced at the surface during degassing. Hopefully they come from hot volatile-rich magma that's losing their volatile. In fact, in the reality, what we obtain is volcanic samples that, instead of having gone directly to the surface, first are interacting and mixing with the hydrothermal system, right? So we're dealing with water-rich samples that have components coming from volcanoes. Obviously, you can already have this, make this prediction that there's going to be a problem, because the hydrothermal waters are going to bring in the volatile mix air-derived nitrogen simply by solubilization, solubility laws. Meteoric water, so rainwater, dissolves some nitrogen from air, and this nitrogen from air is collected in the hydrothermal system and mixes with the nitrogen from the volcanoes, right? So it's very hard, if you don't have a tool, to disentangle nitrogen from air, and that's brought by the hydrothermal waters, and nitrogen from the volcano. Well, that's when our new instrument, the panorama, comes in. This is an instrument that's the largest gaseous source mass spectrometry that exists. There's not many of its kind. Apparently there's two in China. I thought there was only one, but there's two in China, two in the US so far. This instrument is so large that it allows resolving not only the single isotope substitution, 15 and 14N, which is the conventional isotope measurement, but also the unconventional measurement, the doubly substituted 15N, 15N. And this is what I'm going to be talking about today. This is a slide of techniques. We'll not actually describe it in the detail, but if someone is interested in mass spectrometry, I can explain how we did the measurement and how difficult the measurement is actually, but I won't be talking about that. I'll just explain the concept. The reason why we measure 15 and 15N in volcanic fluids is as follows. Here you have a plot of temperature on the x-axis and big delta 30, which is the amount of 15N, 15N, right? 30 is just 15 plus 15. So in this presentation, I will be using the amount of 15 and 15N quantified as big delta 30. You can see on this plot that any thermodynamic prediction would require any nitrogen, any N2 that's made in a geologic process at 1,000 degrees or a biological process at 10 degrees Celsius, or by, I don't know, oil cracking at 200 degrees. This nitrogen is anticipated to have a big delta 30, so the amount of 15 and 15, that's almost negligible. Right? It's a very rare species that we should almost never observe in nature, right? So you end up with 0 per mil, big delta 30 for any nitrogen that's made by a geological process, right? That's the prediction. However, air is here and have a big delta 30 N2 that's extremely enriched, and that looks like a massive disequilibrium. There's almost 20 per mil offset between any equilibrium prediction for nitrogen made by geologic processes and nitrogen that happens to be in air. The reason for this observation is not clear, but it's almost inconsequential to this presentation. Here today, we will be using this disequilibrium to measure, to quantify how much nitrogen is coming from air in a mixed sample, and how much of that mixed nitrogen comes from the geologic degassing of a magma, right? Just to give you a quick idea, you can go to this paper if you are interested in the reason behind this disequilibrium. The group of colleagues that made that discovery at UCLA suggested that it comes from a photochemistry reaction in the high atmosphere of the planet. And that's why there's this disequilibrium in 15 and 15. Anyways, this is all the data that we have acquired during my postdoc. And these data are on hydrothermal samples like the ones that I'm going to talk about in the detail. Just to give you a few words, you can see here on the left axis, the big delta 30. Here is just it's described as big delta 15 and 59. It's the same thing. And on the x-axis is the delta 59, the normal conventional measurement. You recognize the scale. It varies from 0 to 20 per mil. And you recognize here in yellow, air standouts. So nitrogen from air that have been measured almost 20 times across this study. That gives you an idea of the external reproducibility of these measurements. So air is very clearly here, but natural samples show way more variations in terms of delta 59, so on the x-axis, but also in terms of the big delta 30. And that's going to be extremely instrumental in understanding the origin of nitrogen in the volcanic fluid. So here I broke down the data set in 3 types of samples, and today I will be only focusing on the blue samples. Just to give you a quick description, the blue samples are hydrothermal samples. The red samples with the larger uncertainties are actually magmatic nitrogen from a basalt that we were able to extract. And the orange samples are samples from mines and metamorphic environments. I will not be talking about those samples today at all. The point that I'm trying to make here is if you look at the blue samples, you see the massive, this is where most of the variation on the y-axis is occurring. So hydrothermal samples evidently incorporate a lot of air-derived nitrogen, right? You can see this, you can already see the mass balance exercise that can be done to quantify the amount of air-derived nitrogen in those samples. And this is going to be instrumental to understand how much of the nitrogen comes from the water, from the hydrothermal water, and how much does it come from the magma. So I'll be right now talking about just the hotspots. So there's 3 of them, and there's about 30 samples that are shown here. And this is again the exact same plot, but in a different format, because this is extracted from a publication. On the y-axis, still the big delta 30, the same thing. You recognize the scale from 0 to 20 per mil. And on the x-axis, still same thing, the delta 15. I would like to draw your attention on the fact that some samples are yellow, they are from Iceland. Others are blue from Eifel in Germany. And the last ones are red, they are from Yellowstone. These are the 3 types of samples that I will be discussing. what you can see, the first observation, you can see here exemplified by the yellow samples from Iceland. You can have variation of delta 15N at a constant big delta 30. What that means is you can take air-derived nitrogen. You think it's going to have a delta 15N of 0 because that's the value of air. You think it's going to be around here, but in fact, the data show that no, this air-derived nitrogen can move left and right on this axis, mostly left, in fact, and experience isotopic fractionation in what probably is the hydrothermal system. What it means is that negative delta 15N that makes you think of the mantle is not necessarily the mantle. You can have atmospheric nitrogen as shown by the big delta 30 data, right? As shown by our new data. Some air nitrogen can mimic a mantle delta 15N just because of a mass-dependent fractionation in the hydrothermal system. So that is a huge information because that means that if you don't have access to the y-axis, if you're only measuring the x-axis, like most laboratories do, because that's the only, because the y-axis is very hard to measure, you can be deceived and you can be confused by the data. Sorry. So here in Iceland, for example, we do not see any evidence of deep magmatic nitrogen, despite the variation of delta 15N. In fact, this is what we're dealing with. We're not dealing with contribution of volcanic gases to hydrothermal systems. We're only dealing with hydrothermal gases that are being cycled in the hydrothermal systems without evidence for a mantle-derived nitrogen contributing to the system. Negative delta 15N are not necessarily mantle-derived, and in Iceland they're not. So that's something that is, we think, a critical information. In order to explain this this fractionation, it would take me an entire presentation to do that. I'm just going to say that there's one article that has shown that when you take a hydrothermal water full of air-derived nitrogen, right, solubilized in the water, and you put that water at 100 degrees C and you start degassing that nitrogen, you can fractionate isotopic ratios and produce the observation that we made. So we think there's a shallow degassing process involving the hydrothermal waters that led to isotopic fractionation of N2. This is what we think explains the data. Now you can see, obviously, what Iceland does not help describing nitrogen from the mantle because there's no mantle-derived nitrogen there for some reason. But in Yellowstone and Eifel, we do see a large variation in terms of big delta 30, which indicates variable contributions from mantle-derived N2 over there. So that's very interesting because that means that over there, we will be able to constrain the magmatic end member. And the reason why we can constrain that end member is because in this isotopic space, we know we can project the big delta 30 data to a known endpoint of 0 per mil. There is no negative values that exist by design in this plot. So we know that any trend will be projected to a known endpoint. And that's something that is useful for us to extract, for example, the delta 15N value of the magmatic end member contributing to these mixed gases that otherwise you would not be able to constrain. Just to give you an idea, if you were in Yellowstone and you had not measured the big delta 30, the value on the y-axis, you would see delta 15N between 0 per mil. You would think it's air. And you would see delta 15N of minus 12 per mil. You would think it's an extreme new mantle end member. In fact, our data show it's the opposite. The value at minus 12 per mil are the most air-derived nitrogen values, right? They're not a mantle end member. But the value at around 0 per mil is the closest value to the mantle composition at Yellowstone that we assumed was at about 3 per mil. It could probably be 2 or 1 per mil. It's not very well constrained. But it's not minus 12 per mil, that is for sure. So that is something that we find very, very interesting. In those cases, like at Yellowstone and like at Eifel, here we are actually in the situation where we have mixing between some mantle-derived nitrogen and some air-derived nitrogen. And we can decipher what is the contribution of those thanks to our new data. So we can, here this was the slide to say that we can project, and we can find that in fact, Yellowstone, which is a deep plume, has a positive delta 15N. That does not look like air, that does not look like the convective mantle. It would be allowed to think that this positive delta 15N in Yellowstone looks like subducted nitrogen, because sediments and the oceanic crust, they have, remember, anything that comes from the surface has a positive delta 15N. So if you subduct the oceanic crust, or if you subduct sediments, you will predict the mantle source to have a positive delta 15N, right? Well, for that, we have an answer. And we think that did not happen. And this is based on this second isotopic plot that I use. There's only 2 isotope plots that I'm using today. This one is the big delta 30 shown against the nitrogen helium-3 ratio of the samples. Here in this plot, you have air that is known. We know the nitrogen helium-3 ratio is extremely high for air, and we know the big delta 30 is about 20 per mil, right? Because of the way the diagram is created, any mixing here will be on these highly curved mixing trajectories, right? Almost horizontal and then almost vertical, right? That's because of just the way the diagram is built. When you put on that diagram the data from Iceland, this is what you get. You get variation of nitrogen helium-3 ratios, but no indication, no clear indication of deep nitrogen. So it's not straightforward to interpret the data, but when you plot the Yellowstone data here, this is what you get. You get a clear mixing relationship that indicates that the mantle source at Yellowstone, that you remember you can extrapolate to a known endpoint of a big delta 30 of 0. So we know that the mantle source of Yellowstone is going to be around here at 1 million or about 3 to 4 million nitrogen helium-3 ratio. We can basically constrain the nitrogen helium-3 ratio of this source. So here we found a ratio of about 1 million. So there's about 1 million times more nitrogen than there's helium-3 in this primordial mantle source, right? That is not an evidence for nitrogen addition. Why? Because this ratio of 1 million is also the ratio that we observe in the rest of the mantle sources. There's no known mantle sources with a nitrogen helium-3 ratio that's lower than that. That's the lowest ratio you can ever measure. So there's clearly no evidence for nitrogen subduction in this mantle source. That tells us here that we were able to bring some new fundamental constraints on this little cartoon with constraining the nitrogen helium-3 ratio of that primordial mantle source that we think is about 1 million. That is not an evidence for nitrogen addition via subduction. So just to summarize before I go to the subduction zone, and then I will conclude. Air, what we found is that air can fractionate isotopically in hydrothermal systems, which makes things complicated. But thanks to the big delta 30 data, we can disambiguate the complexities of the nitrogen systematics. We also found that helium-3 mantle source can have a high delta 15N, but a low nitrogen helium-3 ratio, as if the role of subduction was not substantial here. So we asked the question of what is the possibility of recording a pre-existing mantle heterogeneity between the mantle reservoirs? That needs to be taken care of. So now in the second part of it's also the last part, because I think I have like 5 or whatever, 10 more minutes. Johnny, tell me if I have less. I can stop right now if you want me to. But if I'm allowed to keep talking, I'll be right now showing the other side of the nitrogen cycle, which is the subduction side, right? We've shown that here in the deep mantle, we don't really see evidence for subduction. Well, what's going on here in an actual subduction zone? So we went to the Central American subduction zone for multiple reasons. One of them is that this is a very well described arc with a lot of studies on the rocks, a lot of studies on the volcanoes, and a lot of studies on the oceanic crust that's about to be subducted. For example, there's two very well characterized drills of these oceanic crusts that are here shown as the yellow stars at these locations. And therefore, the nitrogen concentrations of the subducted components is known, and a nitrogen subduction flux was suggested in the literature. So we took hydrothermal samples or fumaroles throughout the arc, and we characterized the nitrogen helium-3 ratios. Why do we care about this ratio over there? Well, it's because the helium-3 flux, the degassing flux of helium-3 has been characterized in 2002 by Hilton and collaborators. And we know there's about 5 moles of helium-3 that come out of these volcanoes every year. So if we know the nitrogen helium-3 ratio, we will be able to calculate the nitrogen flux that comes out of these volcanoes every year and compare it to the subduction flux. So here is the results for the Central American samples. They are shown in pink. You can recognize the same plot as I used before, and you can still see the same relationships between air, sometimes fractionated air, which would be here, that also seems to occur in arc systems, not only in OIBs. And you can recognize mixing with deep components that appear to have positive delta 15N. So it's confusing because it looks like Yellowstone, right? Yellowstone has a delta 15N about +3. It looks like in subduction zones about the same, it's +4, +5. It's comparable. Now there's one reason to think that it's not the same mantle sources at all. It's the nitrogen helium-3. If you take this previous plot that I've used earlier, you see that mixing relationships with the Central American samples indicate a mantle source that is remarkably enriched in nitrogen compared to a conventional mantle source. The enrichment is about 2 orders of magnitude. So the nitrogen helium-3 ratio is 100 million. So there's 100 times more nitrogen in this mantle source compared to helium-3 than in a regular deep mantle or convective mantle source. That's interesting because we think this is an evidence actually for nitrogen addition in a mantle source, and we can quantify that addition. We know that it's about a factor of 100. These fluids that come out of the subduction zone bring a lot of nitrogen to the mantle wedge that later create the arc magmas. Now, because remember we knew, the flux of helium-3. That means that we can calculate the flux of nitrogen, and we get a flux of about 1 × 10⁻⁻10 gram nitrogen per year. This compares favorably with the nitrogen subduction flux that was 1.6. In fact, we cannot distinguish our estimates such that we cannot exclude that in this subduction zone, the nitrogen cycle is at equilibrium. That means the nitrogen that comes out in the subduction zone entirely comes back out based on the flux estimates that we get. So with this subduction zone study, what we find is 2 things. We find that we can constrain, thanks to our new data, we can constrain nitrogen enrichment in the mantle wedge. That's something that is new. And we can constrain the nitrogen flux, and we find that the nitrogen degassing flux is very similar to, if not indistinguishable from, the subduction flux locally in Central America. So we basically can revisit these fluxes, and we find that in fact, the green arrow must be roughly equal to the blue arrow, such that the nitrogen cycle is not in disequilibrium like the community seems to think. In fact, the nitrogen cycle might be completely in equilibrium with limited exchanges between the surface and the deep earth, due to the fact that the blue and the green arrows, they cancel out. They cancel out each other. So I will conclude by saying that it's a big mess. Now, the nitrogen systematic is not easy because there's a lot of degeneracies and ambiguities. But we think that big data 30 data can actually provide unique, can place new and unique constraints on this cycle by providing fundamental observations on delta 15N and nitrogen helium-3 ratios. What we found, for example, is that variable nitrogen helium-3 ratios, they're not observed everywhere, but when they are observed, they can be linked to nitrogen subduction. And I was supposed to have prepared a very long part of my presentation to talk about modeling, but I won't because it's really complicated. So, and I don't have the time because I took my time. So I guess I'll just end with this question because we don't have all the answers. We're far from having all the answers. And I'd like to bring up this first slide, or one of these first slides that I've introduced today. Well, nitrogen on the Earth has a strange location compared to different types of meteorites. Well, we think that this position is not due to the mixing of extreme end members that over time have provided the composition of the Earth to be somewhere in the middle, starting with the value at -40 mixed with something at +40 mixing. We do not think that it's that happened. We think that maybe if it's not mixing between various types of meteorites, there could be, the community could look into possibilities of planetary processes. And Johnny knows those processes really well, much better than I do. Processes associated with the formation of the core that may fractionate nitrogen isotopes. Processes associated with the formation of reservoirs in the deep mantle that host metals, which also may fractionate the delta 15N of the rest of the mantle. And processes associated with degassing during planetary formation, which, by the way, caused this huge depletion in nitrogen concentration in planets. All those processes might have an influence on nitrogen isotope composition of planetary nitrogen, and we need to look into these rather than focusing on subduction processes that we think are not the cause of the observation. And I will end here. I will take questions if there are any.
Great, thank you very much, Jabrane, for giving the talk. And now it's time for questions. And when you ask a question, please first let us know your name and your institution. So, Tiemo, so feel free to open your mic and ask a question.
Hello.
Hey.
My name is Montian. How to pronounce your name?
You would say Jabrane. Americans like to say Jabrane.
Yeah, right.
You can call me Jab.
Oh, by the way, I'm from University of Bern in Switzerland. And I'm not a geochemist, but it's interesting to see this talk. My first question is, how do you estimate the bulk nitrogen content of Earth and Mars?
The nitrogen concentrations of the mantle of the Earth?
No, the bulk Earth. You show in the first image, you have chondritic composition and also Earth and Mars.
In this slide, it's very poorly explained. I'm sorry, I apologize. This is here concentrations of chondrites versus concentration of the mantle of the planets. Okay. We do not know the concentration of the bulk Earth.
Right.
We don't know the amount that's in the core. We don't.
Okay, so if, we consider volatile conservation during Earth's creation and you disregard the contribution from Earth's atmosphere, then the conclusion about extreme nitrogen depletion of Earth relative to chondritic materials is not robust, right?
It might still be robust. It might still be robust because if you take, for example, the partition coefficient that we think are correct for nitrogen distribution with metal and silicate, they're not huge. It doesn't look like there's a lot of nitrogen.
What about atmosphere? You consider only mantle of Earth, but atmosphere has a large reservoir.
Great point. I had a slide, I removed it because it was taking me too much slides, but there's basically the number of moles of nitrogen in the mantle is something like 10 to the 20 moles. And in the atmosphere, it's something like 2 times 10 to the 20 moles. So there's only a factor of 2 that you get when you add nitrogen from the atmosphere. Because remember, there's so much nitrogen in air, but air is such a small mass compared to the mass of the mantle.
I see. Good. I have a second question if you have time.
I have all the time.
Good. Would you go back to your slides about the Yellowstone, those clouds with many dots?
Which one would you like to see? This one or the
further back? This one, yeah. So I see the diamond-shaped data point. That's for air, right? It has the value, a single point, and then you have a trend of Yellowstone data. You are trying to explain this Yellowstone gas composition by mixing, am I right?
You are correct.
And if it's mixing, then what about the x-axis? I mean, y-axis shows a mixing between 20 and 0, but x-axis, I mean, I'm expecting the air composition will be at delta 19, delta 15 at the upper left corner, and that big diamond shaped at the lower right corner, then that forms a mixing line. But if it is mixing, then it should simultaneously explain the nitrogen isotope value and also the big delta 30.
The data here point towards multi-component mixing. Here, I'm not sure exactly understood. Air is here, right? That's what we know, but we have no a priori knowledge on what air-derived nitrogen is in the hydrothermal system, because in the hydrothermal air can fractionate isotopically. So we think that air was, to begin with, was here, and because of some fractionation in the hydrothermal system, there's a component that got there, and there's an unknown component that got here. And, but only this one was mixed with the deep nitrogen.
Okay, I see. So there is a hidden assumption that from your shown data point of air-derived nitrogen, there's some fractionation, and then the fractionated gas mixed with the Yellowstone gas.
Exactly. And look, this is not totally even, because we here, I had a slide that said that there's a kinetic isotope fractionation between air and dissolved N2 in water. And this is what we think. There's a fractionation that also explains these points here at Iceland. It also explains here this point in Hawaii that I didn't talk about because it's not very constrained. So yes, we think that the data demonstrate, not us, but the data demonstrate that there must be some fractionation of air in the systems.
Okay. By the way, would you remind me how do you define the big delta 30 of nitrogen?
It's the amount of 15N measured relative to the expectation of a stochastic distribution.
I see. Okay, good. That's all for it.
Before you conclude, I would say, are you in the same institution as Martin?
Which Martin Jones?
No, Martin Schiller.
I don't remember. Sorry, I'm in the physics department. So.
Oh, okay. So he would be in the geochemistry. Okay, my bad. Okay, thank you.
Sure, thank you. It's an interesting talk.
Thank you very much.
Okay, next question, please.
Hi.
Hi.
Hi, this is Mang Lin from Guangzhou Institute of Geochemistry, Chinese Academy of Science. So very nice talk. And so my question is about your crumb isotope in MOBs. So they're all negative. So do you think it's fractionation or it's just the value of the mantle? How do you think about that?
Hold on, which ones? Which samples are all negative?
MOBs, the mantle values,
yes.
the triangle.
Those ones, great question.
Yes.
This was a very limited amount of data that we have because it's very hard to measure MOB for reasons that I can explain in the detail, technical reasons. We think that they're negative here just because that's the normal composition of the convective mantle that is at about -5 per minute. So we were actually, when we got those data, relieved to see that we can obtain the correct expected delta 15N for a mantle reservoir with MOBs. So yes, the answer is yes.
Okay, okay. By the way, is it the convection mantle, the delta 15N value is due to subduction or other process?
For what reservoirs?
For the convection mantle.
For the primordial mantle?
The convective mantle.
The convective mantle.
Yeah.
For the convective, that's a great question. That's basically, we think that it isn't. We think that it's not possible to explain the composition of the convective mantle by subduction. And this was explained in the diagram that has, but that didn't have time to show, but that's basically explained in this diagram. If there's subduction for 4.5 billion years, you can never reproduce the composition of the mantle. And this is here very quickly shown in the red curve. That's the modeled composition of the convective mantle that we know is -5. And when you make it exchange with air, you always get positive delta 15N at the end. Whether the starting composition is -40 or whether the starting composition is +50, it does not change. You always get a wrong mantle value if you make it exchange via subduction. So we think it's not possible.
Okay, thank you. Cool.
The next question, please.
Yeah, hello. I'm Nejun from Tokyo Institute of Technology.
Hi, Nejun.
I have same question about this. If you show this figure, I just want to ask, because you calculated it's impossible because you use a subduction isotopic fractionation with plus value.
The isotope fractionation is...
Or the subduction, yeah.
So it's the big delta of the subduction. It's not exactly a fractionation. It's the average value of the delta 15N of sediments compared to... and if you look at this, if you look at these, you see that the delta 15N of sediments through time, they are mostly between 0 and 3 per mil on average compared to air. So we think this is a robust choice to make.
Okay,
so here, subducted components, it's written on the graph, subducted components have delta 15N 3 per mil higher than bulk surface nitrogen.
But as far as I know, this value is based on the current observation of the sediment. But if you look on the early Earth before the GOE, that time I just worried some abiotic process will be give very depleted value.
We don't see those values. This is the delta 15N of sediments. This is here the GOE. You get one huge excursion here at 2.7, but other than that, you don't see any very negative values. It's very constant. There's this one extreme possibility here of maybe strange metabolisms that took place here, but there's no trend that indicate there was negative values in the past. Okay.
Yeah, and another question is also related to this topic. Yeah, from your model that the mantle is nitrogen is mainly primordial, that only 20% contribute from the air. But if you consider your model is right, that means the early Earth has the nitrogen, similar to the current atmosphere. But if that is the case, based on the partitional fractionation, that the nitrogen is very easy to come into the air other than in the magma ocean. So in that case, if the primordial mantle is around, for example, 80% of current amount, that means that the early Earth atmosphere should have nitrogen maybe 100 times than current. Do you consider that possibility?
No, we don't think that. I mean, we've modeled, in fact, the nitrogen concentration in the reservoirs. And first of all, there's no evidence that the nitrogen concentration of air was higher in the past than it is now. In fact, if anything, there's evidence it was lower. So there's less nitrogen in the past than there is now, based on the few evidence that we have. And the papers are here. You can see Avis 2018 and Marty 2013 and Ishizawa 2007. You might know these papers. And we found that, in fact, you need to constrain see this is here, the modeling, to constrain the quantities, we know that the air concentration has not changed. If anything, it has not decreased. It might have increased, but it has not decreased. In order to understand these and to model these, to fit this observation based on natural data, you have no subduction, no exchange. That means that the concentration of nitrogen in air has not changed through time. There's no reason to think that it would be 100 times larger in the past than it is now, because there's no evidence that this nitrogen was subducted anywhere.
Yeah, but actually the nitrogen is very low solubility in the magma ocean is compared to the air. Yeah, so we are just consider if we use some data we already have, we can calculate that value. But as you suggested, it's not possible.
I think I see what you mean. You mean if there's a magma ocean, it would produce a primordial atmosphere, and that primordial atmosphere would be the, so that is a great question, but for that we would need to know the FO2, because the solubility of nitrogen depends on FO2 a lot. And if the FO2 of the magma ocean was IW -2 or -3, which I think Johnny would think it's not extreme, it's not crazy, well, or even IW0, the nitrogen would not be that degassed. There would be a lot of nitrogen staying in the magma ocean. So that is a really great question. And I think one of the ways to understand it, this is a great question, really, I'm serious. It's to constrain the nitrogen-argon-36 ratio, because nitrogen and argon have the same solubilities for IW0 + 2 + 10, but under IW, the solubilities change. So maybe we can track degassing processes this way by looking at the nitrogen-argon-36 ratio in the future. I agree with you. It's a great question.
Yeah, thank you. Yeah, I have a last questions, but it's not related to nitrogen calamine stove, but it's related to your recent paper about methane calamine stove. Yeah, because now I'm working on methane calamine stove. I'm also interested in the abiotic methane. So in your paper, you said that in the hydrothermal system, the DD clumping can be re-equilibrium, reordering. So if this could be the real case, so how about your thinking in how can we apply this in the nature samples if DD depleted signal can be disappeared even at very low water situation? So in the future, how do
methane? Yeah, for methane.
Sorry?
You're asking for methane, for CH4?
Yes, methane, the DD clumping reordering.
DD clumping reordering. Yeah, well, I mean, I don't know. I really like, it looks like the DD clumping in methane is fragile. My real question right now is we have observed reordering of DD clumping in methane in hydrothermal fluids. That will be my paper. But there's also another paper in basins where we see reordering of DD based on either abiotic processes or AOM, which is, the anaerobic oxidation of methane. So there's a lot of processes that seem to reorder clumping. So my question is, for the future, why do we ever see disequilibriums? There's situations where basically it's not reordered, while I think reordering is actually the norm. In most situations, the DD should be reordered to the temperature of the environment, but sometimes it's not, and it keeps these disequilibriums, and I don't know why. Why is this maintained in Kid Creek? I don't know. Why is this maintained in some weird basins? I don't know. I think it's a great provocative question for the future. I don't know with who you're doing the methane, but there's a lot of work to do on that, and if you work on that, that would be great.
So we should first explain what happened to this re-equilibrium or reordering methane, find the reason, and then we can apply later.
Well, we think we found a reason. We think that the symmetry numbers give us understanding of why one of the isopod reorders more than the other. It's not a perfect reason, but we think we found one. And we will need to find experimental reasons to also address that. But again, the bonding strengths between CH4 and deuterium is not huge. It's not very hard to reorder.
Yeah. Okay. Thank you for your answer.
No, thank you for your great questions.
Thank you very much. Yeah.
Great. Do we have one more question from the audience?
Hi, this is Ben from Zhejiang University, and I'm curious about your panorama. Is stable for the NLS, and is a duplicate sample or standard stable? And how long do you get one data from the pre-treatment to the NLS?
So what we do, we measure the blue peak, the amount of the blue peak. You can see how flat and beautiful it is compared to the red peak. And this is extreme. I mean, you can't find something that's more stable than this instrument, in my opinion, such that you would measure for 7 hours one sample. So that's the time it takes to get a good error bar. Measure 7 hours, and the error bar, which over the measurement during the 7 hours, does not change. That means that the stability over the 7 hours is constant. It's very constant. For air, the reproducibility, you can see it here. It's about, the symbols are really huge here. So it looks like it's big, but it's about 0.3 per mil in 2 sigma. In 2 standard deviations, the reproducibility of the external, it's an external reproducibility, it's 0.3 per mil. The internal reproducibility of a sample measured multiple times, the same sample measured multiple times, 0.1 per mil. It's very, very good. It's the external that is a little, I mean, of course, a little not as good.
Okay, thank you.
So you see here, there's a huge error bar on the lower part. This is one of the mobs that I was asked about before, and these ones have very little nitrogen concentration, so we could measure only for 20 minutes because after 20 minutes there was no more nitrogen, and so of course 20 minutes measurement mean much larger error bar. So it really the error bar really depends on the time of the measurement, and it's between 20 minutes minimum, 7 hours maximum.
Okay, thank you.
No, you're welcome. Thank you.
Okay, thank you very much, Jabrane. And
thank you.
Okay, thank you for giving talk, and thanks to everybody for participating. Okay, have a good day. And our next talk will be Wenbo from Caltech on topic of ocean seismic thermometer. And the talk will be on, let me see, November the 29th. Okay, I will send you more information by email or by WeChat message. Have a good day, everybody.
Bye, everyone. Thank you.